All right, then let's just jump into nuclear chemistry. Okay, so here we go. We're going to start out like we always do with the conceptual stuff, right? We're in chapter 11. This is nuclear chemistry. Now this chapter is really different than anything else we've done in the class, with the exception of basically chapter 3 when I introduced you to atoms, right? Because after we introduced to atoms, we talked about chemical bonding and chemicals and chemical reactions of all sorts. But the nuclear chemistry is chemistry that happens in the nucleus of the atom. So we're not concerned with what's happening on the surface with the electrons. We don't care how they're bonding with each other or how they're reacting. Instead, we're really kind of focused on just the atom itself. So just to remind you guys what the atom looks like, we've got, and this is a very simplified version of it, simplistic image, right? But you have the nucleus, which is the center of that atom, which is the dense middle. It contains the protons and the neutrons. Protons have a positive charge and neutrons have no charge, but they both weigh 1 atomic mass unit, right? So these are both 1 AMU. And the electron is on the outside. The electrons are on the outside in these shells, as we talked about it, shells and subshells and orbitals. And because they're on the surface, they dictate the chemical behavior of the atom. They have no mass. That's not to say they have no mass, really. They have relatively little mass as compared to the proton and the neutron, right? So the proton is, on the neutron, weigh about 2,000 times as much as the electron. So you should know that electrons absolutely do have mass, but that just as compared to the protons and neutrons, that mass that's added by the electrons essentially gets rounded off. It's not significant in terms of the significant digits that we report. So essentially 0. Do you guys remember this? Okay. All right. So what we're focused on again, because this is nuclear chemistry, we're going to direct all of our attention right here. It's all totally different from what we've been doing before. And in there, of course, we have the protons, neutrons, and collectively they're called nucleons because they're the particles that are in the nucleus. Okay. Now, we did learn that atoms of the same element can have different numbers of neutrons, right? That changes the mass, but not the identity. Now, if you have a different number of protons, that changes the identity, right? So that defines what an element is. So if I have 6 protons, I am carbon by definition. If I have 7 protons, I am nitrogen by definition. But if I have 6 neutrons, that just means I add 6 weight. It doesn't mean that I'm carbon or nitrogen or anything like that. So, so that's what we do. We add up the nucleons to find the mass, but the protons define the element. I just want to remind you guys of that. Write this down. Neutrons contribute to mass. Protons determine the identity of the element. Okay. And what we find is that some isotopes, you guys remember, I'm using all these words that we just haven't used this entire semester. Okay, isotopes are atoms of the same element with a different mass, which means a different number of neutrons. Do you guys remember this? So for instance, you could have the carbon 12 is the most common, which is of course why the average mass weighted for abundance of carbon is 12.01. But there's also carbon 13. That's about 1% of all carbon is carbon 13. And there's even some carbon 14. That's the radioactive one, right? So here are 3 isotopes of carbon, and this is one way to show it, right? You can say carbon 12 or C12. This indicates that it's a carbon isotope with a mass of 12. Another way to do it that we did is you could put it in the upper right-hand corner, usually much smaller, right? That would show you the mass. These are 2 different ways of expressing that. And of course, you could always just say carbon 12, right? All of these are ways of saying the isotope of carbon with a mass of 12. And of course, you can look up carbon on the periodic table. You can see carbon has 6 protons by definition, which means that carbon 12 has how many neutrons? So if carbon 12 has a mass of 12 and 6 protons, that means that carbon 12 has 6 neutrons, because 6 plus 6 gives you 12. And that carbon 13 has how many neutrons? 7 neutrons, good. And carbon 14 has how many neutrons? 8 neutrons, perfect. Okay, now, what makes a nucleus stable or unstable? That is, if it's unstable, then it's likely to undergo some sort of nuclear reaction. It has to do with the ratio of protons to neutrons in there, for reasons that are a bit beyond the scope of this class, all right? This gets into nuclear physics, and I am not a nuclear physicist. I'm afraid I'm gonna butcher it if I go into a lot of detail, but we do find that there is a band of stability, as they call it, in terms of the ratio of the number of protons to the number of neutrons in the nucleus. At the low end, like carbon is a small molecule, we find, generally speaking, you want a 1-to-1 ratio of protons to neutrons. But at the high end, like up at uranium, it does better if it has about a 1 to 1.5 ratio. So if you had, for instance, 60, or if you had 80 protons, you might want 120 neutrons, for instance. Does that make sense? To balance that out. And you can see that in the periodic table. In fact, let me pull that up right here, just so we can have a reference here. Hopefully you can kind of see these masses. I'm going to zoom in. You can see, okay, carbon, which is element 6, it has 6 protons. The average mass weighted for abundance of carbon that we find is 12. So it looks like it has about, on average, 6 protons for every 6 neutrons. You'll see the mass doubles here for each of these elements in like the second row. But if you're looking down at something like platinum, which has a mass of 78, now it has it has 78 protons. You can see it's got 195 for its total mass. Whoa, hello. So it has 107 neutrons. So divide that by 78. You can see it's like 1.4 times as many neutrons as protons. And we predict that it's going to need more neutrons to kind of buffer those protons, because protons have a positive charge, so we expect they will repel one another. So the neutrons kind of take up space in between those positive charges, so they don't repel one another. We can keep the nucleus together. Does that make sense? Semi, sort of, maybe. Okay. Now in this class, you'll never be asked to predict what nucleus will be radioactive and what will not. All right. Which one would decay, which one will not. We're just going to talk about different types of decay. And if you know the type of decay, you can predict the product. But that's just kind of an understanding as to, what makes one thing stable and another thing not. Like carbon 12 is not radioactive. It's not going to decay on you. But carbon 14 definitely will at a prescribed time, like predetermined time. This is what carbon dating is based off of. Our knowledge that carbon 14 has a half-life of about 5,700 years. And when that tree dies, it's all the carbon 14 in the tree is going to start decaying, and you can see how much is left in the tree and determine when it died. Does that make sense? Okay. So this is just kind of our background. Now, I've got our fundamental differences of nuclear chemistry versus traditional chemistry that we've been doing, okay? So nuclear chemistry involves the nucleus. That's weird. Never done that before. Everything else we've done involved these electrons, whether they were being shared in covalent compounds or given away as in ionic compounds, right? We find that different isotopes react in different ways. Some won't react at all. So it's weird. Carbon-12 won't react as a nuclear chemistry thing, but carbon-14 does. All right, that's different, right? Because if I'm doing a reaction where I'm burning gasoline or sugar, my chemical reaction doesn't care whether it's carbon-12, carbon-13, carbon-14. They all behave exactly the same thing. It's the same way, which is why, for instance, in nuclear medicine, somebody can give you some glucose sugar that is built with, say, carbon-14 molecules and give it to you, and it can end up in your brain because your brain loves glucose sugar in order to work. And then they can image your brain to see what's going on inside of your brain based on the radioactive thing that they just put in there, right? But the carbon-12 wouldn't do that. All right. The rate is not dependent on and is unchanged by pressure, temperature, and catalyst. So we talked a lot in chapter 7 about rates of chemical reactions and how you could change it. You could speed up the reaction, usually if you heat it up. You could change the direction of a reaction if you added pressure, if it has gases in it. Catalysts make reactions go faster. All of these things are external things that basically affect the surface of that molecule or the atom. And the nucleus is shielded from all of that. The nucleus feels none of that. Doesn't feel temperature changes, doesn't feel the pressure changes, doesn't feel the catalyst changes, because it's just affecting what's on the outside. And so everything we learned in chapter 7 about rates of chemical reaction doesn't apply to nuclear chemistry. So that's kind of interesting. We find the nucleus decays whether the atom is in its elemental form or in a compound, right? If that atom is ready to decay, it will decay, it'll fall apart, it'll react no matter where it is. Because again, it doesn't care what's happening on the surface with its electrons. It's the center that's falling apart. So whether that carbon atom is in a sugar molecule, doesn't matter, it's gonna fall apart. Or if it's in its elemental graphite form, it'll fall apart. Zach says, what makes an elephant all of a sudden start decaying? And again, that takes us back to the ratio of protons to neutrons gives it a certain measure of stability or instability. So this guy is never going to start decaying, where this guy might. Now, you and I cannot look at a specific atom and say, oh, that one's about to go any minute. No, we can't do that. We can look at a sample of atoms and predict based on what we know about them that, oh, at any given time, a certain percentage of them is going to be decaying. If that makes sense? But you couldn't look at that inside the nucleus and say, this is the one that's about to go. At least, so far as I know, that was my understanding of the nuclear physics most recently. That could change in the next 20, 50 years. Who knows? So we can predict that something might decay because it is in a relatively unstable nucleus, but we couldn't say this one's going to go. Does that make sense? And the last thing that's different about nuclear chemistry as opposed to traditional chemistry is our energy levels for nuclear reactions are enormous. Okay, so here's my comparison, 1 gram of gasoline versus 1 gram of uranium-238. As a fuel, uranium-238 is 28.3 million times more energetic, gram for gram, right? So this is why nuclear energy is considered to be so much cleaner than other energy forms. Not because it doesn't produce any waste, but because it's so energetic that you can get a lot more energy out of it as compared to the little amount of waste that can be produced. So I love this as a really good comparison. And this is just for fission as well. Fusion is also excellent and cleaner. So those are the differences between nuclear reactions and chemical reactions you should know and understand for the test. Okay, we have 6 different types of nuclear reactions which you need to know for the test and need to be able to apply. And let's just briefly go over what these are and how we represent these, and then we'll take a little break, okay? So I'm going to scroll down here. Okay. Types of nuclear reactions that you need to know. So for these first 3, what we see is that something is being emitted or kicked out of the center, that nucleus. So these things are being emitted from the nucleus. These are sometimes also called decay, so alpha decay, beta decay, positron decay. And sometimes you'll also see them spoken about as radiation, like somebody got alpha radiation or there was beta radiation. And you'll also hear about gamma radiation. I'm just going to put this down here. Radiation. Okay, so the difference between emission, decay, and radiation as we use these words, these are all describing the same process, but kind of from a different point of view, right? So the atom, the nucleus decays, and when it decays, it might emit or kick out a particle. And if you receive that particle, then you are exposed to radiation. Does that make sense? Just going to kind of break this down, because you'll hear all of these words used almost interchangeably. And they don't mean exactly the same thing, but they mean pretty much close enough to the same thing that they're all referring to the same process, right? So the nucleus decays, and usually if it does it by one of these things, when it decays, it emits a particle. That's emission. And radiation is if you are exposed to the emitted energy or particle, then you receive radiation, right? All right, so that's, you'll hear all of these. I'll use them just interchangeably, but I'm talking about the same process. All right, so alpha decay proceeds by alpha emission, and if you are next to it, you will receive alpha radiation. Beta decay decays by beta emission. If you're next to it, you'll receive beta radiation. Positron decay proceeds by positron emission, and if you're next to it, actually, you're going to receive gamma radiation. So I'm going to put this up here. Actually, hang on. Okay. All right. Now, let's talk about the particles that we're going to see. Like, what is an alpha particle or a beta particle? Well, these were named before we had a really good idea what was actually what the atom was made up of, right? So we weren't sure about electrons, protons, neutrons. We had no idea what these were, but we recognized that something was happening with the radiation. And so they were named before we knew that. But an alpha particle, as we now know, is actually a helium nucleus. It has a mass of 4. It has a charge of +2, which means it has 2 protons and 2 neutrons. So it's just like a helium atom, essentially. It's a helium nucleus. That's what an alpha particle is. Okay. Okay. Now, the beta particle, which I haven't actually shown here, is the electron. Again, we had no idea what hang on, is electron. So we didn't know what the beta particle was. We didn't know what the electron was. So, but now we know it's a beta particle. So beta emission is kicking an electron out of the nucleus, and beta radiation is basically a stream of electrons. Okay. And so that's the alpha and the beta. Now the gamma, and this is the symbol for gamma right here. Put this down here. The gamma radiation has no mass and it has no charge because it's not an actual particle, it's just energy, pure energy being released. So it has this symbol here, okay? And you already know, we know electron, proton, neutron, alpha particle is new, a positron is going to be new. There's a mass of 0 and a charge of +1. It's like the opposite charge of an electron, but has the same mass as an electron. And the gamma radiation is new. And we're going to use these symbols to kind of express them. And the symbol, remember, for each of these symbols, we're going to have the mass in the upper right-hand corner, and in the upper left-hand corner. And in the lower left-hand corner, traditionally, that's where we put the number of protons. And since we're not necessarily looking at protons anymore, we're going to call it number of positive charges, like protons, but not necessarily protons. Okay, so the mass on top, positive charges on the bottom. That's what each of these symbols is referring to. So this 0, 1, -1 is telling us that the mass is 0. Now that's not exactly 0, it's just rounded off to 0 as compared to these other masses. It has a -1 charge, and the symbol is E for electron. Sometimes, in fact, Master Chemistry does this. They'll actually call this a beta minus. And they'll usually do it that way too. Beta minus particle. Oh. Here. All right, so a neutron has a mass of 1 but no positive charges. A proton has a mass of 1 and 1 positive charge. Helium has a mass of 4 and 2 protons in it. The positron has a mass of 0 and 1 positive charge. Again, mastering chemistry is going to call this, sometimes they're going to call it beta plus radiation instead of beta minus. And then that's the gamma. Okay, so Zach asked a question like, is gamma the most popular? What's going on with this? And not necessarily. What you have to look at is what your exposure is and what your body does with that and how you protect yourself from that, right? So these are common decay types that are going to shoot some sort of particle out at you that might collide with you, and you might need to protect yourself from. And you'll see that some of them are heavier than others, right? Alpha particle has a mass of 4, so that's really big and heavy. The beta particle, the electron, it doesn't have a mass of actually 0, but it's much, much smaller than the alpha particle. And that gives it more penetrating power, right? So the alpha particle, that can be stopped by your clothes, right? A lab coat is sufficient to stop an alpha particle, and you wouldn't be worried about that. A piece of paper could stop that. The surface of your skin, which is dead skin cells, will stop an alpha particle. So you wouldn't be too worried about alpha particles if you're talking about exposure to the outside of your body. As opposed to a beta particle, because it's so much smaller, it can penetrate up to like a centimeter. So you would need a little bit more shielding than for a beta particle to take care of that. The problem with the gamma radiation is that it has no mass. And so it's really, really hard to block. This is where you're going to need a concrete wall or a lead sheet kind of a thing, a thick lead sheet to protect you from gamma radiation, because the penetrating power and therefore the potential power to damage your tissues is much higher. Does that make sense? So the smaller the mass, the higher the penetrating power. In fact, I'm going to write this down. So smaller, whoa, I'm still in symbol. Go. Smaller mass equals higher penetrating power, right? And so that doesn't necessarily mean, I mean, it does mean that it's potentially much more dangerous, right? So as Zach says, you have to wear lead in the operating room when the X-ray is being used, right? Because the X-ray, light gamma radiation, has no mass, it has no charge, it has high penetrating power. That's why you use it as an X-ray. But the gamma radiation is actually more energetic than the X-ray. It does have to do with the wavelength or frequency. In terms of the gamma radiation, it does, at least, because it is energy, so it travels like light, right? It travels with a wavelength. Whereas, of course, your alpha particle and your electrons, them being matter instead of just pure energy, it has less to do with the wavelength and more to do with the mass that gets stopped by other matter. Does that make sense? Okay. Now, so gamma is more penetrative than alpha is more penetrative than beta. Now, that's not to say that alpha and beta radiation can't be used or they couldn't be dangerous. And in fact, one thing that I ask you to do in this lecture, and you'll see on the discussion forums, is to go look up some forms of nuclear medicine, because nuclear isotopes and nuclear chemistry is used a lot in medicine in ways that you wouldn't even expect, right? And so you might take, for medication, you might take an alpha emitter or a beta emitter orally, or you might have it administered into your veins, right? And with the hope that it's going to end up at a tumor, and your tumor is going to be bombarded with alpha and beta particles, and it's going to cause damage to the tumor, and the tumor will go away, right? Or you might be given a gamma emitter, essentially, and that'll go into your brain, and they're going to watch where the gamma rays come from to see what kind of activity your brain is doing at any given time, right? Is there a part of your brain that's not functioning the way that it's supposed to? So we use it in imaging, we use it in treatment pretty extensively. You would be surprised, unless of course you've had one of these things done and then you're like, oh, I'm not surprised, I've done that before. But it's really been used in remarkable ways. And one of the ways that the chemistry, I think, makes our lives better. So you'll see that from interior as well as exterior exposure. Obviously, you wouldn't want to consume one of these if you weren't being treated specifically for a disease that could cause problems. Because the energy, basically, as these things get emitted, it's called ionizing radiation. In fact, I'll write this down here. Ionizing radiation. And this is when your emission or radiation knocks electrons off of molecules in your body, and so they become ionized, right? They become positively charged, and then they react with their surrounding tissues, and it basically just destroys your tissues, which is obviously not a happy thing, essentially. Oh my gosh. Hang on a second. Erica is exactly right. I don't know what. The beta has higher penetrating power than the alpha. I'm completely backwards here. Okay. There we go. Okay. So we're going to start looking at specific examples of these types of nuclear reactions: alpha emission, beta emission, and positron emission. Okay, so just to scroll down here. So alpha emission is radiation or decay where the nucleus emits an alpha particle. Okay, no surprise there. The alpha particle has 2 protons and 2 neutrons. It's basically a helium nucleus. And that's why it's written as that 4-2He right here, right? Okay, so to give you an idea, here's an example from the lecture notes. Uranium-238 can decay by alpha emission, just like this. So here's your first example. So uranium-238, now I'm always going to put, in this chapter, we're always going to put the number of protons down here. That's by definition. So I should, just by saying you know that it's got 92 if you look it up on the periodic table, but nobody wants to look it up on the periodic table constantly. So we're just going to always, like, just to remind ourselves, this is the number of protons in each of those, okay? So uranium-238 with 92 protons, because it's uranium, decays by alpha emission. So it kicks out this alpha particle, which is a 4-2, and 2 makes it He. And then what remains is the nucleus has 234 total mass and only 90 protons. Then you look at the periodic table and you'll see, okay, 90 protons is right here, thorium, okay? And what I want you to note from this equation is that your masses are conserved, right? The total mass stays the same. You have 238 for your total mass on the left-hand side of the equation, and I have 4 plus 234, which is 238. I have got that on the right-hand side of the equation as well. And the total positive charges are also totally conserved, right? 92 positive charges on the right-hand side of the equation is equal to my 2 positive charges on the helium plus my 90 positive charges from the thorium. Do you guys see that? Okay, so based on that observation, you know that your masses and your positive charges must be conserved. You can predict the product of any alpha emission equation. So here's another one. If I say polonium-208 decays by alpha emission, and I say what else is made there, you should be able to tell me. What is the new mass of the particle going to be? It's going to be 204 because 204 plus 4 is 208. And then the number of positive charges is going to be 82. 82, because 82 plus 2 is 84. Good. And then you look on the periodic table and say element number 82 is lead, Pb. So this must be 204-82 lead. How'd you guys feel about that? Okay, not too bad. Everything's conserved. I could give you a problem with that on the test. Now, I'll be honest, I might make it a little harder. Instead of writing it like this, I might say polonium-208 decays by alpha emission. And you're going to have to say, okay, this is what polonium-208 is. Decays by alpha emission, that's what their alpha particle is. And then you're going to have to fill in that last piece. But otherwise, it's kind of simple math. It's pretty straightforward. It might even be kind of fun. Like Sudoku, but better. All right, so that's alpha emission. Next we have beta emission. So beta emission, and this one the nucleus emits a beta particle, which is basically 1 electron. Yeah, Sudoku chemistry. Now, at this point, you guys should all be very concerned. There's something wrong going on. because I'm telling you that the nucleus is kicking out an electron. And you might say, hang on a second. Wasn't like the fundamental thing that we learned is that the electrons are out here and there's not any electrons in the nucleus. So where's that nucleus coming from? That's bizarre. What even is going on here? Okay, well, beta particles are electrons, yes. They do not come from the electron cloud. They come from the nucleus. And what they come from is the decay of a neutron. And again, particle physics is a little bit beyond the scope of this course, so we're not going to go into detail about the structure of neutrons and protons. But essentially, you can hopefully see that if you have a neutron, let's see, I've got a neutron here. It's got a mass of 1 and a charge of 0. And if I kick out an electron, which has a mass of 0 and a charge of -1, all right, what will remain? Whatever remains is going to have a mass of 1, right? Because my total mass has got to add up here. And 0 equals -1 plus a +1, or just 1. So what particle has a mass of 1 and a charge of +1? A proton. Yeah. In this process, essentially, in beta emission, one neutron in the nucleus gets converted into a proton. Remember what we talked about, how the reason that these decay is because that ratio of neutrons to protons is off, right? Is unstable. And so if you have too many neutrons or not enough protons, here's a really convenient way to get rid of a neutron and get an extra proton and hopefully move towards stability. If you can decay a neutron by kicking out an electron, and the electron says, whoa, I don't belong in here, I'm an electron. So it gets kicked out of the nucleus altogether. And that's the beta particle or beta radiation. Then you will have converted what remains into a proton. Does that make sense? I mean, kind of. It's still really weird though, right? Like, I can explain it, but the fact that the nucleus is kicking out electrons should still be like, okay, whoa, this isn't regular chemistry anymore. This is in fact nuclear physics. And I encourage you, if you think this is cool, you should take a physics class, nuclear physics class, and would be really interesting. Okay, so iodine 131 decays by beta emission. Just gonna kind of spread this out so you can see what's going on here. And just like we predicted, you've got a mass of 131 on the left. In fact, I'll write this down. And that's equal to the total mass of 131 from the xenon plus 0 from the electron, right? And down here you have 53 positive charges on the iodine. And that is equal to the 54 positive charges on the xenon and a negative charge from the electron that ran away. Okay. Now, Sarah says, should we memorize all the symbols? Well, yes, you should memorize all of these symbols, right? You should already know the electron, the neutron, and the proton, although we haven't necessarily looked at them from this perspective, but you know their relative masses and charges. And that's just helium. Positron and the gamma one is the only one that's going to be really new, but seeing them in this perspective maybe is different, so you should definitely memorize those or be able to put them together. Whereas, of course, the rest of these, like 234, 90th, this is what you get when you do the math. You shouldn't memorize those. Okay, let's do another one. Carbon 14 actually decays by beta radiation, beta emission. what else is made? Okay, Erica says we've got a 14 on the top because we've got 14 equals 14 plus 0. Good. And a 7. Sarah says a 7 on the bottom because 7 plus a -1 gives me a 6. And then element number 7 is in nitrogen. Good. Did you guys see that? Now don't be, this is really tricky, right? It's easy to look at that as a positive 1 instead of a -1, but it really is a -1. So you're not going to get a 5 here, you get a 7. And this is the radiocarbon dating that I was talking about previously, where we know that the half-life of carbon-14 is about 5,700 years. So by looking at how much carbon-14 remains after a certain amount of time, you can tell how old something is. Interestingly, you can't use radiocarbon or radiation dating methods in anything that's younger than about 70 years because the multiple radiation tests or nuclear tests that have been done around the world have caused kind of low-level radioactive fallout, which kind of garbles those tests and gives you wrong results. So it's kind of an interesting thing. Okay, that's beta emission. Any questions on beta? Okay, so the last thing we've got here for today is positron emission, and then we're going to do a couple examples, okay? Well, if that's going to be a rabbit hole for you, David, I would love it if you could post about it in the discussion forums. Because I haven't gone down that rabbit hole yet myself. I just think it's really interesting. All right, so here we go. The nucleus emits a positron. This is a beta plus particle. I'm never going to test you on that, but Master Chemistry will talk about that. So this is a positron emission, and you might say, now wait a second, what is a positron? Oh, okay. Sure, whatever. Looks like an electron except it's positively charged. Great. Again, not in the nucleus. Where is it coming from? Well, can you guess what in the nucleus might decay by kicking out a positively charged particle? The proton. The proton has a positive charge. The neutron doesn't have a positive charge. It would be hard for it to kick out a positive particle. But in positron emissions, essentially you have a proton which decays by kicking out the positron. Now again, no significant amount of mass is lost, but you do lose the positive charge. And what remains? The neutron. That's right. What remains is something with a mass of 1 on the top and a charge of 0 on the bottom, right? Because 1 equals 0 plus 1 and 1 equals 1 plus 0. And our particle with a mass of 1 but no charge is a neutron. So this is kind of the opposite of the beta emission, right? So beta emission says I have too many neutrons and not enough protons. If I convert a neutron to a proton, maybe I'll have a little bit more stability for my cluster of protons and neutrons in here. Whereas this is the opposite. It says I've got too many protons as compared to neutrons. And maybe if I could convert a proton to a neutron, then my ratio of protons to neutrons will be better. So this is what it kicks out. Now, you might have heard of alpha radiation and beta radiation and how you protect yourself from that, but nobody's heard of positron radiation. Might have heard of positron emission, but not positron radiation. And the reason for that is the positron is actually, oh, hang on a second. Excuse me. That's an E because it's a positron. Okay, positron here. The positron is the antiparticle to the electron. What does that mean? That it's the antiparticle. Yeah, not just that it's the opposite. Although it's clearly, I mean, it kind of looks like the opposite. I mean, it's the same in terms of mass. It's the same in terms of size. It's the opposite in terms of charge. But being the antiparticle, what I mean by that is, I mean, like matter and antimatter, right? If electron is matter, then the positron is the antimatter to it, right? The particle, exact, equal, and opposite. And what happens when matter and antimatter collide? Okay, they cancel each other out. Yes, that's one way of describing it. The way they cancel each other out is by obliterating each other. Right? You guys have watched Star Trek, right? When matter and antimatter collide, there's a big explosion, right? Or in this case, they will destroy each other, and their mass, or matter, is converted to energy. And there's actually an equation for that, although we totally don't have to know this equation. But if you've ever heard this equation, the energy that is created when you destroy matter, and generally speaking, I mean, this is one of our fundamental tenets of the atomic theory. Matter is not created or destroyed in chemical reactions. That's true. This is not a chemical reaction. This is a nuclear reaction. So matter can be created or destroyed. And the energy that is released when matter is destroyed is equal to the mass of that matter which is destroyed times the speed of light squared. Okay, now Sarah says, wait, they have no mass. Oh, they totally have mass. Remember, the electron and the positron, they have a zero mass as compared to the proton and the neutron, because it's so small it gets rounded off. But that is actual mass, right? It's about 1/2000th. As compared, or you could say 5/10,000ths. And yeah, this is Einstein, right? Equals mc squared. That you can convert between energy and matter. Sure, it's really hard, right? There's only very special cases where that actually happens, but when the positron gets released from the radioactive nucleus, it has to travel through that cloud of electrons right here. Has to travel through the cloud of electrons to get out, and it never gets out, right? The positron gets released, it hits an electron, the two of them are destroyed, and instead you release pure energy in the form of gamma radiation, right? So it's positron emission, but what you actually get is gamma radiation. So we have 0, -1, electron, encounters my 0, +1. I'll call it an electron, but really it's a positron now because it's positively charged, right? And this just feels like it's right out of Star Trek, doesn't it? Matter and antimatter collide to form energy. And you're like, whoa, unexpected Einstein, right? Gamma radiation. Okay, so this is what you actually get. Now this is the basis for positron emission topography. Whoa, let's forget. Or the PET scan is an imaging scan that uses a positron emitter and administers the positron emitter, and then it scans for the gamma rays that are produced in the place that you're looking for, whatever it is that you're looking for. Okay, but this is an imaging that uses this form of nuclear radiation. So isn't that cool? Okay. Let's give you an example here. This is a great example. Potassium-40 decays by positron emission to form argon-40. Now, of course, in the end, you don't see the positron. In the end, you see the gamma radiation. But we're only going to show this first step because that way you can see, hopefully, pretty clearly this part where you've got 40 mass is equal to 40 mass plus 0 mass. And on the bottom here, we've got 19 positive charges, and that should be equal to 18 positive charges plus 1 more positive charge, right? Okay, so positron emission topography, like a PET scan, it's used to look for a number of things. I've seen it in a brain scan is where I've seen it previously, but I know that's not the only thing that it could look for. But because the brain, if you want to see like what areas of the brain are active, like after a stroke, as Erica noted, or after a brain bleed, if you're like, okay, is this part of the brain tissue, is it still active and functioning, or was this damaged by the stroke or the brain bleed? Then they'll administer a positron emitter that will go in the brain, and then they'll just kind of scan for activity, right? So if this particle makes it into that section of the brain, then the blood is getting there and there's probably activity there, right? But if it doesn't, then there's not any activity in that part of the brain. There's no, there might be damage there, if that makes sense. So that's what a PET scan does. You know what I like about this example is that it's potassium here. Potassium-40 is actually like the most stable form of potassium, and it's still radioactive. It's radioactive enough that high potassium foods like bananas have a measurable amount of radiation that they emit. And you, as a person with potassium inside you, you emit a measurable level of, like background. You might call it just background radiation at that point. But I mean, who thought that bananas were radioactive, right? That's kind of fun. Kind of a fun thing. Okay. Well, here's the one. Carbon-11 decays by positron emission. This is the one that's used in the brain PET scan. So they use carbon-11. They make glucose out of carbon-11 because carbon-11 still makes glucose just like any other carbon. And then it decays by positron emission and while your brain's consuming the glucose, and you can see the other thing there. Sarah says, is the radiation, is that why potassium's lethal? No, potassium's lethal because it will upset the potassium-sodium balance for your channels, and essentially if you get too much of it, you'll have a heart attack. That's why a large dose of potassium would be lethal. But the amount of radiation you get from a banana, we do not suppose is causing you significant damage or harm. Certainly, I mean, you need potassium to live because, again, sodium, potassium pumps, right? So, as pre-nurses, you guys know kind of a scary amount about things that will kill you. But yeah, potassium is sometimes used, isn't it used in lethal injections sometimes? Okay, Erica says 11 on top, 5 on the bottom, because 11 equals 11 plus 0, and 6 equals 5 plus 1. We can just look at our periodic table and confirm element number 5 is boron. Excellent. So when carbon decays by positron emission, you get boron in there. There we go. Yep. So that is positron emission. All right, how do you guys feel about these three? Okay, then let's look at your worksheet. We're doing the first page of your worksheet today, and I kind of glossed over the first section. I will let you do that. The first section is just a review. Let me pull this over here. This first section is just a review where you're identifying how many like protons and neutrons and nucleons using these numbers, right? And then this section is what we're going to do today. And it is identifying what kind of emission is occurring and filling in the blanks. Now, each of these is either beta, alpha, or positron. So just the three that we have already covered, right? But if I take away your little cheat sheet here, can you remember, can we fill in the blank? All right. So the test is very similar to this, Erica. Yeah. It's kind of fun. Again, it's like chemistry Sudoku. The challenge is that students are so freaked out by chapter 10 that they spend all their time studying for it, and then they kind of forget to like make sure that they're still good on the chapter 11. So sometimes they'll miss a few here and then they feel really bad about that. So don't do that. But otherwise, okay. First, let's go assign these. What kind of emission is this? Alpha, beta, or positron? This one's alpha emission because you see the 4,2 helium that's formed. Okay, good. What about this one down here? Yeah, that's an electron, so that's beta emission. Good. What about this one? Good. Electron, again, so it's, again, beta emission. This guy? Positron, good. Positron emission, and then this guy, alpha, and then this guy, beta. Excellent, okay. All right, and over on this side, what do we have? Alpha, good. And this one? Positron, good. This one? Beta. And this one? Alpha, good. And this one? Positron, you guys are doing great. And this one? Beta. Whoops. Okay. Excellent. Well, that wasn't too bad. Let's fill in the blanks. So when francium-208 decays by alpha emission, what else does it make? (204) on the top because 204 plus 4 is 208. 85 on the bottom because 85 plus 2 is 87. And element number 85, Sarah and Nicole tell me, is astatine. We can triple check that, but feel good about that. All right, yeah. Okay, what about this beta emission? What do we get? All right, 3 on the top because 3 plus 0 is 3. Add 2 on the bottom because 2 minus 1 gives me 1. And element number 2 is helium. Excellent. Good. Okay. What do we have here? Yeah, 24 on the top because 24 plus 0 is 24. 12 on the bottom because 12 minus 1 gives me 11. And element number 12 is magnesium. See, it's almost like a Zen-like experience, isn't it? Everything is right with the world. 18. 8 plus 1 is 9. Element number 8 is oxygen. Good. What about this guy? Curium decaying by alpha emission. 241 plus 4 is 245. Good. And 94 plus 2 is 96. And that's going to be plutonium. Here we go. Right? Plutonium 94. I believe you, but verify, right? There we go. Okay. This guy here, 131 on the top, 54 on the bottom, and element number 54, that's xenon. There we go. And here we go. Platinum 190. Let's see, 186 plus 4 is 190. 76 plus 2 is 78. Element number 76 is osmium. Excellent. What about the positron emission of arsenic 74? Okay, 0 plus 74 is 74. 32 plus 1 gives me the 33. And element number 32 is the germanium. Okay. What goes on top here? We've got 0 plus, that's going to be 32 is 32. 16 minus 1 gives me the 15. You guys are really fast. You're doing great. All right. 235 equals 4 plus 231. And 92 equals 2 plus 90. And element number 90 is thorium. Excellent. Next. Good. Oh, you're quick. Okay. So 0 plus 13 is 13. And 1 plus 6 is 7. And that's going to be carbon. And finally down here, 0 plus 60 gives me 60. Negative 1 plus 28 gives me the 27. And element number 28 is nickel. Okay, how do you feel about that so far? Nice, good. Okay, now there's one extra step that I haven't taken here that you might see in your homework, and that is a element, specifically like really heavy elements. Once you get kind of big, you just kind of fall apart anyways, but very heavy elements might undergo multiple decays to get to a stable element. That's called a decay series. And so if you see in your homework that there's a problem where you have a decay series that happens, then you actually don't have to identify each stop along the way. If I say this undergoes 4 beta and 3 alpha decays, you can just put it out and say, here's my, my reactant, my initial thing undergoes 4 beta decays plus 3 alpha decays plus what? And you can play the same game that we've done here, where you just say the total mass here equals the mass of 4 beta particles plus the mass of 3 alpha particles plus whatever mass is left. And of course, the number of total positive charges equals the number of positive charges in 4 beta particles plus the number of positive charges in 3 alpha particles plus the amount here, whatever's left. And that hopefully is not a big stretch for you guys. But otherwise, I think that the homework should be pretty straightforward. And I hope you enjoy this. This chapter is, I told you it would be a little bit nicer than chapter 10. And that's why I really like it where it is here at the end of the semester. It gives you kind of a very soft landing while your brain is still wrapping itself around acid and base chemistry. So with that, I'll let you go and I'll see you guys next Tuesday. We'll do more of this.